All right, welcome everyone to my 7.4 bonus video here. In this video, we're just going to go right at it, solve a problem. And before we get into this, I'd like to kind of pause here for a second, and I would like you to take this problem and kind of imagine this shows up on your quiz or your exam, right? During chapter 7, we're learning a whole lot of different techniques on ways to evaluate out integrals, right? Before we just had U substitution, and that was it. Now we know integration by parts, we know trigonometric substitution, we know powers of trig functions, sines and cosines, secants and tangents, all that sort of stuff. And now we have partial fractions. And so we have a lot of tools at our disposal. And yet, many times when I have seen exam questions or quiz questions or things like this, you see wording just like this, right? It just says evaluate. It doesn't say use trigonometric substitution or use partial fractions, things like this. And so quite often, one of the hardest parts about this is trying to decide, how do I know when to do what? And we will certainly spend time in 7.5. 7.5 is a section called strategies for integration and talking about when should you be doing what. So to some extent, I'm asking you to kind of preemptively think about this problem and kind of identify, how do I know that I should do X, right? Should it be just a U substitution? Should it be integration by parts? Should it be trigonometric substitution? Things like this. Imagine this question comes up on the exam. Take 2 minutes here, decide, what do you do with this? All right, so I hope that you've paused the video and you've given this some thought. So this actually does live in, partial fractions section, but it's a little bit sneaky here, right? You actually need to do some stuff beforehand in order to get it into this good form where you see kind of, again, partial fractions is all about rational functions, right? Polynomials divided by polynomials. And so in order to get this set up, to see these polynomials divided by polynomials, the claim is that I need to do a U substitution first. And this is kind of classic, right? Many times we've done a U substitution where U is equal to the stuff in the denominator. And so if I try this, U is equal to this kind of inside function, the stuff inside of the denominator in this case, then we're going to get du is going to be equal to e to the x dx. And so we can go ahead and rewrite this a little bit, right? So I'm going to do an integral. And let's see, I'm going to have 1 over u. And then instead of dx, I'm going to write du divided by e to the x. And so we can see that I've transformed a lot of this in terms of u's, but I haven't gotten it all, right? And so I need to go back and take one more cycle. And again, with any u substitution, you need to get everything in terms of your new variable u. And so, okay, let's go back and I see my kind of exchange rate here. I know that I can trade in 1 plus e to the x for u. I have an e to the x remaining that I need to swap out and get it in terms of u's. And so, well, in this case, I can go ahead and rearrange a little bit. And I can get e to the x is equal to u minus 1. And so then I can go ahead and swap that in. 1 over u, 1 over u minus 1 times du. Now, whenever you do a U substitution, right, you always have options as far as what you do with the bounds. You can either drop the bounds, like I'm doing here, consider it an indefinite integral, right, which is just, again, an integral without these bounds here. Go ahead and solve that, substitute in back for x, and then plug in those bounds. The other option is that you can change those bounds to u values, right? Right now they're x values because of this dx right here. If you wanted to, you could change those bounds to u values, and then that's what you would plug in for u. So I think the last time we encountered this sort of situation in one of these bonus videos, I left them as x values and kind of did this all the way through and then swapped it back in. This time, why don't we switch those bounds to u values, right? So I'm going to go ahead and swap these. Oops, accidentally erased my du there. So at the base value here, the bottom bound, right, we have x equals 0. And I would like to get a corresponding u value for this. So I'm going to go ahead and plug this in to my u equation up here. And I get u is equal to 1 plus e to the 0. Because after all, we're plugging in 0 for x. And this gives us the corresponding u value of 2, right? 1 plus, well, e to the 0 is 1, so 1 plus 1 is 2. So the corresponding thing that goes with u here is going to be 2. Now, for our upper bound, we have 1, so x equals 1. This corresponds to 1 plus e to the first power. And that's just, well, 1 plus e. Can't really simplify it more than that. Don't want to really use our calculator and round too early here, I guess. So even though we could plug this into our calculator and get some decimals here, I'd be wary about rounding too early. So this is where I'm going to leave it here. By the way, maybe we like to see, we have these fractions times fractions. We can certainly combine the denominators, combine the numerators, right? 1 times 1 is going to be 1. And now it really looks like the partial fraction setup that kind of we're used to. Okay, now that we have this, we really see the need for partial fractions, right? We have a rational function, we have polynomials divided by polynomials, rather boring polynomial on top, just 1, and the polynomial on bottom is already nicely factored for us, right? U times u minus 1. And so I'm hoping that there is a way to rewrite this, right? Where we have a divided by u plus b divided by u minus 1. So again, that these are nice kind of linear terms. They're similar to x and x minus 1, right? But we're just using a different variable here, u's in this case. And so we use our partial fractions decomposition that we brought up in class, and we know it should look something like this. And so let's go ahead and solve. Again, we're trying to choose this good a and b value. So that way it would be equal to 1 divided by u times u minus 1. And so in order to find that good a and b value so that these are equal functions, I'm going to go ahead and multiply through by this LCD, right? So the lowest common denominator, u and u minus 1, and we're going to do that across the entire thing, all the terms, both sides of the equation. And when we do that, right, well, in this first term, we would have the u's would cancel out, right, on top and on bottom. And so we'd have a, and the u minus 1 does not cancel out. For our second term, when we distributed this to the b bit here, the u minus 1s would cancel out, but the u's would not. And then finally, in our last piece on the other side of the equation, right, well, we would have perfect canceling and we would just be left with 1. Now we're going to go ahead and range this and grab all of our linear terms, right, with the u to the first power and all of our constant terms. So we're going to have a u plus b u minus a is equal to 1. And I'm going to put a plus b times u minus a is equal to, and I'm going to write this rather suggestively here, right? So this, we have 0 u's plus 1. So again, kind of, we just have 1 over here, but I'm going to write this kind of in a similar polynomial fashion where we have kind of this linear bit here, and we want it to match up with the linear bit there. And then we have the constant terms. So with the constant terms, we can just see very quickly that negative a has to be equal to 1. And so therefore a is equal to negative 1. With the linear terms, this gives us the equation that a plus b needs to cancel out and give us 0, right? We don't see any linear terms, any u's on the other side, right? By comparison, right, if you had something like u plus 1 in the numerator, right, that would be perfectly fine. But then, right, again, you would have u plus 1 right here. You'd have u plus 1, right? And then so you would have 1u plus 1 sort of deal. So that could certainly happen as well. But again, we have kind of a very simplified version where we don't have any u terms. I just want to remind you that this could happen, right? And it's just because we have kind of this very nice thing that that's why you don't see any u's over there. Okay, so if a is equal to negative 1 and a plus b has to be equal to 0, then we know that b is got to be equal to 1. So that means that we can go ahead and rewrite this, thanks to our partial fractions work here, as the integral from 2 to 1 plus e of, and again, a is supposed to be negative 1 and b is supposed to be 1. Now we can go ahead and integrate this. So when I integrate, we're going to get negative the natural log of the absolute value of u plus the natural log of the absolute value of u minus 1. And we need to evaluate this from 2 to 1 plus e. And remember, those are u values. We plug them in for u. So let's go ahead and do that. We're going to plug these in for u. Let's see, the absolute value of 1 plus e, well, it's already positive. So I'm just going to write 1 plus e and forget about the absolute values there. And let's see, 1 plus e minus 1. So this is going to be the natural log of the absolute value of e. Oh, excuse me. But again, e is already positive. So we really don't need the absolute values there. And better yet, we know from our calculator, right? If we plug in E into our calculator, if I plug in the natural log of E into my calculator, right? This is going to tell us that this is equal to 1. So there's a nice way to simplify that. Okay, so now I've successfully plugged in 1 plus E into all of these things. Now let's go ahead and plug in 2. So we're going to have minus the natural log of the absolute value of 2. Again, 2 is already positive, so those absolute values aren't doing a whole lot. And then plus natural log of the absolute value of 2 minus 1 is going to be 1. And again, plug that into your calculator, you'll find that this is equal to 0. So the natural log of 1 is equal to 0 here. Let's go ahead and maybe just simplify things out. One more line, negative the natural log of 1 plus E plus 1 minus a negative, so plus natural log of 2. So this right here would be my final answer. We could, of course, plug this in to our calculators and get some decimals and round that to 3 decimal places if you'd like. Again, notice that I waited until basically the very end in order to plug that in. You don't want to be rounding early, right? Otherwise, you would miss out on, for instance, right? You wouldn't see this natural log of E right here if you had rounded that E. And you'd get something quite close to 1, but it wouldn't have been equal to 1. And so again, kind of hold off on rounding until the very end. All right, so again, the recap here is that even though at the kind of the starting of this, it didn't necessarily look like our classic partial fractions, right? By doing a U substitution first, we got something that again kind of then was very similar to our classic partial fractions that we learned about here in 7.4, and we were able to solve that using our traditional partial fractions method. So again, kind of you needed a little bit of a U substitution up front here, and this one worked out. All right, I hope you got something from this video, guys. Good luck on the upcoming quiz and everything. Again, 7.4 isn't on this quiz, at least not this week's quiz. So at the time of recording this, it's not on quiz 5. So yeah, anyway, I hope that you guys enjoyed. And if you have any questions, post them on Piazza. I'd love to help. See you later.